All right, so here we're looking at a Maclaurin series for another function. It says find the first three non-zero terms in the Maclaurin series for f of x equals e to the x times ln of 1 plus x. This might feel similar to an example that we already did, where we were looking at x squared times, what was it actually? It was this example right here. We found the Maclaurin series for x squared times sine of x, and we saw that all that we had to do was multiply an x squared to each term of our Maclaurin series for sine of x. This is a little bit different because neither of these factors in this product are x to a power. They are each functions that have their own Maclaurin series. So what I'm going to do instead is I'm going to write the Maclaurin series for each one of these in place of where they appear in that product. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. Natural log of 1 plus x. If we write that out term by term, it's going to look like x minus x squared over 2. Remember, this one alternates. Plus x cubed over 3. No factorials in my denominators for this one. Minus x to the 4th over 4 plus dot dot dot. Okay? It's not asking me for the answer in summation notation. It's just asking for the first three terms of this Maclaurin series. So here's the way I'm going to do this. I'm going to start with the lowest possible degree term and try to figure out if that will show up in this Maclaurin series, and if so, what will it look like? So we can multiply two Maclaurin series in the same way that you multiply a polynomial. You can take the first term in this series here and multiply it to each of these terms in this series over here. Then I can move on to the next term in this series and multiply it to each of the terms over here. Whatever I got from that first step can be added to whatever I got in that second step, and I'm getting, the terms of my power series. Obviously, you can't do this for the entire series because there's no time to multiply infinitely many terms to infinitely many terms. But since we only want the first three non-zero terms, I'm going to think, what is the lowest possible degree term that I can get in a power series? It's a constant term. In the process of doing these different products, will I ever arrive at a constant term? Well, in order to do that, I would need a constant term over here times a constant term over here. In any other pairing of terms, I'm going to get at least one factor of x in there. There is no constant term to choose over here, so I won't end up with a constant term in this product. What is the next what's the next highest degree? Well, I can get first degree terms, x to the power of 1. 1 times x would give me a first degree term. Will I get any other first degree terms in this product? Well, using this 1, the answer is no, because 1 times x, I already did that. 1 times x squared over 2. Now we're looking at x squared terms. That's too high of a degree. And I can see that as I keep moving to the right, the powers on these x's gets bigger and bigger and bigger. So I'm not getting any x terms from that. This x right here, can I multiply it to anything over here to get an x term? And the answer again is no, because I would need a constant term over here to multiply to that x to get an x term. So this x from this product is the only first degree term that I'm going to get. Now, will I get any x squared terms? Well, I can see that if I do this 1 times this negative x squared over 2, I will get an x squared term, negative x squared over 2. But if I multiply that 1 to anything else, I'm getting something other than an x squared term. Let's move on to the next term in this left series. X. Can I multiply that x by anything over here to get an x squared term? X times x would give me x squared. But notice that x times anything else over here would not give me an x squared term. Moving on to x squared over 2 factorial, I would need a constant term over here to multiply that to get an x squared term. We already know that's not there. So that means that the only x squared terms I get from this product are these two. Okay? Now, I know we have 3 terms here, but those would combine into a single x squared term. So we need an x cubed term if we want 3 of them, if an x cubed term exists. So 1 times x cubed over 3 is an x cubed term. Notice that 1 times any of these other terms will not give me x cubed, so I move on to the next term. And here's where you might notice a helpful little pattern to make this process go more quickly. I took a constant times an x cubed term. By going up to the next highest degree term here, I need to go down to the next lowest degree term here so that the product comes out to x cubed. So as I move from left to right in this series, I'm going to be moving from right to left starting here in this series. 1 times x cubed over 3. X times negative x squared over 2 is minus x cubed over 2. And then moving to the left and moving to the right, I have x squared over 2 factorial times x, which is plus x cubed over 2 factorial, which is the same thing as just 2, plus dot, dot, dot. These will combine so that I have x plus x squared minus x squared over 2 is just 1/2 x squared. And then notice the x cubed over 2 that's negative here will combine with the positive version here, giving me a 0. That leaves me with just 1/3 x cubed plus dot, dot, dot. So this is a process for multiplying two Maclaurin series together. It's a little bit lengthy, but when we notice that pattern where we're moving from left to right here and right to left here, making pairs, that helps this to go a little bit quicker. If we can multiply two series together, we should also be able to divide series, which we can do. That might be a little bit intimidating to think about, but it is a thing that we can do. So what does division of series look like? Well, if you remember how polynomial long division works from algebra, and if you think of power series as just really big polynomials, it's the same process. So in this example, we want to find the first 3 non-zero terms of the Maclaurin series for f of x equals tangent of x. And the way that we're going to do this is not directly. We could, find a bunch of derivatives for the tangent function, plug zeros in for all of those, get our coefficients that way, just like we did for the sine and the cosine function. The problem is that the tangent function does not have a repeating sequence of derivatives that the sine and the cosine function had. It gets more complicated the more derivatives that we take. So instead, I'm going to think of this tangent function as sine over cosine. And then I'm going to use the Maclaurin series for each one of these. So sine, of course, is equal to x minus x cubed over 3 factorial, which is 6. So I'm going to use the actual values here, 6. Plus x to the 5th over 5 factorial, which is really 120, minus dot, dot, dot. I only need those first 3 terms there. Cosine is equal to 1 minus x squared over 2 factorial, which is just 2, plus x to the 4th over 4 factorial, which is 24, minus dot, dot, dot. That's plenty. Okay, so now we're going to do polynomial long division, but with these series. So if you remember how that works, long division, I'm doing this numerator divided by this denominator. The thing I'm dividing by goes on the outside. 1 minus x squared over 2 plus x to the 4th over 24 minus dot, dot, dot. And then up here is where my quotient will go. Down here is where where my dividend goes, the thing I am dividing into. So x minus x cubed over 6 plus x to the 5th over 120 minus dot, dot, dot. Okay, now I know a lot of people will get intimidated by long division, and especially polynomial long division, but the process is actually fairly straightforward. So I'm looking at this term here in my dividend, the first term, and I'm comparing it to the first term in my divisor, and I'm saying, what would I need to multiply that 1 by to make an x? Well, x times 1 is x. Now I take that x and multiply it to each of these terms. So I get an x minus x cubed over 2 plus x to the 4th times x would be x to the 5th over 24. And then I take all of these. Notice there's going to be a dot, dot, dot in there, but I'm only writing the first 3. I need to subtract all of those. X minus x is 0. So that's supposed to happen. This should cancel out. Negative x cubed over 6 minus negative, so think of that as plus x cubed over 2. You're dealing with fractions here, so it's 1/2 minus 1/6 effectively. We get 1/3 x cubed. x to the 5th over 120 minus x to the 5th over 24. You're subtracting those fractions. This would simplify to 1/30th x to the 5th. I'm not showing the work on the fraction addition because I don't think I need to do that. I think you guys can work out how I got 1/30th here. All right, so that would be the result of this subtraction here. Next thing I want to do is take this first term that I arrived at here and ask, what can I multiply this 1 by to make this 1/3 x cubed? And of course, that would be plus 1/3 x cubed. And then I repeat this process, 1/3 x cubed times each of these terms. So I'm going to get 1/3 x cubed. 1/3 x cubed times negative x squared over 2. So you notice I'm going to get an x to the 5th, and then 1/3 times negative 1/2 is negative 1/6. So I get negative 1/6 x to the 5th. Because I didn't write any more terms up here, I don't really need to bother working out any more of these terms here because I'm not going to be subtracting them from anything in particular. We subtract all of that. These will cancel out, of course, and then this turns into negative 1/30th plus, because that minus will change the sign there, 1/6. That comes out to 2/15 x to the 5th plus dot, dot, dot. Okay, now at this step, I repeat one more time. Notice I'm saying, what would I multiply 1 by to make 2/15 x to the 6th? Of course, that is 2/15 x to the 5th, x to the 5th. And then I could go and do the subtraction, but at this point I have what I need. So I'm just going to say plus dot, dot, dot. And that's the first 3 terms that I was asked for. So I can say that the tangent function, tangent of x, is equal to x plus 1/3 x cubed plus 2/15 x to the 5th plus dot, dot, dot. Notice, kind of like what we noticed for the sine function, all of the exponents that I'm getting here are odd numbers. And we also know that the tangent function is an odd function. So that is what we should expect to happen. We should expect only odd degree terms here. I'm not going to prove that tangent of x equals its Maclaurin series using Taylor's inequality, because like I said, we just did that for a couple of examples, and then you can kind of work out the other ones. But these two things are in fact equal to each other. So there is yet another Maclaurin series that we can use. Okay, now that's technically it for section 11.10, but there's one thing I wanted to throw in here that's extra, because I don't feel like I could teach the subject of Taylor series and Maclaurin series without talking about this. This is one of the coolest results. It's something called Euler's formula. So in this class, Calculus 1 through Calculus 3, actually, we're dealing with functions of real variables. We don't deal with functions of complex variables. If you remember, complex numbers are numbers of the form a plus bi, where I is the imaginary constant. But there's a very, very rich and a very, very huge area of mathematics that deals with functions whose inputs can be complex numbers. We call those functions of a complex variable. The larger study of that topic is called complex analysis, and that is an upper division and graduate level course in math. In those courses, you would talk about Euler's formula. It would be one of the first things that you talk about because it's one of the fundamental tools that you use in complex analysis and the study of functions of a complex variable. And now that we've gone through the topic of Maclaurin series, we can actually show where this comes from. So if you think about it, the exponential function e to the x, the trigonometric functions sine and cosine, they seem to have no relationship to one another. They come from completely different places. The exponential function usually first arises in the topic of compound interest and financial math. Sine and cosine comes from trigonometry, where we're dealing with geometric concepts, triangles and circles and measuring angles. They seem to have no relationship to one another. Euler's formula shows that they are actually very, very closely related. So the way that we do this is we look at the Maclaurin series for those functions, e to the x, sine of x, and cosine of x. And we define functions from these familiar ones where we're basically extending their domain into the complex numbers. So we're saying if I know what it means to do e to the x, I know that, the number e is approximately 2.7 something. I can raise that to a power. That's what e to the x means. But what if that thing that I'm raising it to is a complex number? What does it mean to use a complex number as an exponent? Well, we can define e to the z, where z is allowed to be a complex number, by just taking the Maclaurin series for e to the x and replacing that x with a z. So now we're assuming that the z here can be any complex number. And remember, the complex numbers include the real numbers as well, because in this form, z equals a plus bi, if b is equal to 0, then I have z equals the real number a. So real numbers are just a subset of the complex numbers. Sine of z can be defined as its Maclaurin series, but replacing the x with a z, so that z can now be a complex number. And we know what it means to raise complex numbers to integer powers. We talk about that in trigonometry. We talk about shortcuts for that. So now I have definitions for e to the exponential function, the sine function, and the cosine function, which allows me to plug complex numbers in to those functions. And what I want to do is show that they are related to each other. I'm going to do that by specifically plugging in ix into my exponential function, where x is assumed to be a real number, so that ix would be an imaginary number. So if I did that, here are the terms, the first few terms of my exponential function after plugging ix in. So remember, the exponential function looks like 1 plus x over 2 factorial plus x squared over 2 factorial plus x cubed over 3 factorial and so on. But all of those x's I'm replacing with ix's. Now, if it's been a while since you've looked at imaginary numbers, remember that I to the power of 1 is just I squared by definition is -1. I cubed is -1 times another factor of I, which would be -I. I to the fourth is -I times I, which is -I squared, or -1, or +1. And then if I raise I to the fifth power, I'm just multiplying by another factor of I each time. And if you notice, I'm right back to where I started. So raising I to integer powers like this gives me this cycle of 4, I, -1, -I, 1, and so on and so forth, okay? All of my even powers are going to be either positive or -1. So when I go through this and I look at my even powers, ix squared is the same thing as -1 times x squared. Ix to the fourth, since I to the fourth is 1, I to the fourth here is going to just give me a +1 there, x to the fourth over 4 factorial, and so on and so forth. All of the odd powers, ix cubed, ix to the fifth, will give me a positive or a negative I. We're seeing that in this pattern here. So ix stays as an ix. Ix cubed becomes -I, and then x cubed over 3 factorial, and so on and so forth. So this is what I get by plugging ix into the exponential function using its Maclaurin series. If I were to group up all of the terms that don't have i's in them over here, and if I were to group up all of the terms that do have i's in them over here, and then factor that I out, notice that this is what I would get. Only the even-powered terms have no i's in them. And notice also they're alternating. 1 -x squared over 2 factorial plus x to the fourth over 4 factorial. Over here I would have a -x to the sixth over 6 factorial. So I get this alternating series of these even-powered terms, but I recognize that as just the cosine function. That's the Maclaurin series for the cosine function. Over here, when I group up these odd-powered terms that have i's in them and factor the I out, notice I end up with the Maclaurin series for the sine function. So this is the same thing as cosine of x plus I sine of x. That leads to this formula right here. In order to evaluate e to the ix, I just do cosine of x plus I sine of x. But remember, we assumed x was a real number, so evaluating that cosine and that sine is not a new thing. We know how to deal with that. Euler's formula opens the door to evaluating exponential functions at complex numbers. That's its primary purpose. But it ends up being useful for a whole lot of other things the higher you go. Now that by itself is pretty cool, but of particular interest is when we plug a certain value in for x. If I plug a pi in for that x right there so that I get e to the pi I can evaluate it by plugging pi in for these x's here. Cosine of pi plus I sine of pi. Cosine of pi we know is equal to -1, and sine of pi would be 0, so this evaluates to just -1. E to the pi I equals -1. I could also add that 1 to both sides to get this. E to the pi I plus 1 equals 0. This form of this result is known as Euler's identity. And as a mathematical result, it doesn't have like super far-reaching implications. It's more what people oftentimes cite as an example of beauty in mathematics. And the reason for that is because it's a very, very simple equation. It involves the 5 most important constants in the entirety of mathematics, which is 0, 1, pi, e, and the imaginary constant I. Every single one of these constants you can think of as coming from a completely unrelated part of mathematics, and yet all 5 of them are intimately related by a very, very simple equation involving only one addition operation and one exponentiation operation with a product, pi times I up there. So this is a very unexpected result because, again, all 5 of those constants do not seem like they should be related since they all come from different places, and yet somehow they are. So that's where I'm going to leave this section. We have one more section to cover, but that will be significantly shorter.